All right. So, Fred, 772. Do you know how to solve this one?
Um, let's see. I might have some ideas.
All right. Okay. So, what does it mean there that this business here, CaO, calcium oxide plus chlorine gas, producing this compound here? What does this delta H mean?
Well, that delta H means how much energy is, because there's a negative sign, how much energy is released from that process? Heat energy.
Yeah, that's right. How much heat energy is released from that process? Good. And then this equation here, which is a little long, so it gets broken up, right? This is how much heat energy is what? Required or released?
The negative sign means released, right?
Yeah, released. Good. And then this one, this reaction here.
That's how much the energy is released.
Oh, but there's a positive sign.
Oh, I mean required.
That's right. Good. And then how are we going to calculate the energy associated with this one, right? It doesn't give us this one. So how do we calculate it?
Well, if you add the first two together, for example, first two equations.
You mean this one here and that one?
Yeah. Then the resulting heat for the sum of those equations is the sum of those two heats, right?
That's right. Good. So the simple principle that we kind of just always remember is that if I have, and this is kind of an easy way always to remember it, if I have there we go, a chemical reaction where A and B are coming together to form C, and if I have a delta H associated with this, let's say that's 100 kilojoules or whatever the units are, well, I know that if I put a 2 in front of all of these, there's twice as much energy. It's now going to become 200, right?
Yeah, so what?
Well, essentially what that's doing is taking this chemical reaction that has a delta H of 100, and it's like adding to a second chemical reaction that has a delta H of 100. And so the sum of these two reactions, which I'm not going to rewrite it here because it's just this up there, would be the sum of those heat energies. Okay? So what we need to do, another thing, another way you can think about it is if I take this and instead of summing it, I multiply it by 2, right? That's what we did there. We can also reverse it. We know that as well, right? C reversing to A plus B. What's the delta H for that reaction?
I can't remember.
Well, it's just this reaction reversed, right? So.
Oh, yeah, okay, so it's negative 100.
That's right, negative 100 kilojoules or whatever the units are, okay? So, using those principles, we can look at this chemical reaction here that we want to have and see if we can add or reverse or multiply by 1 or 2 these chemical reactions to get this one, okay? So, I want chlorine gas. Where am I going to get the chlorine gas from these chemical reactions?
Only the first one has chlorine gas.
That's right. Only the first one has chlorine gas. This has 1 mole, but I only want a half a mole, right?
So what do you do?
Well, I don't want to times this one by 2, but I'm going to need to divide it by 2, right? Because I only want to have 1/2 chlorine gas. I don't see the chlorine gas anywhere else. Do you?
No, it's not there. It's only the first one.
Okay. So I could tell that I'm going to have this one, this reaction here, with the chlorine gas on the left side, but it needs to be half as much. So I'm going to write that new reaction down. So I'm going to write 1/2 CaO plus 1/2 chlorine gas, yielding 1/2 calcium OCl2. Okay? And what is the delta H for this reaction?
It was a negative 110.9.
Right. So what is it now?
Well, do you just divide it in half?
That's right. So I'm going to get this. Whoops, turn on that light there so we can see the calculator. I'm going to get the negative 110.9 and divide by 2. Let's try that again. Negative 110.9 divided by 2. Okay, so negative 55.45. Okay, now how did I know that that's what I wanted to do? How did I know I wanted to take that first equation and divide it by 2?
Well, you said that you were looking at the final equation and you saw we needed a half a chlorine gas, right?
That's right. That's how we knew that we needed to do that, because we need to get this from somewhere. And in those equations that were provided, this is the only one that had the chlorine gas. Okay. How about the NaBr? Where do we get the NaBr from?
That's in the second equation. Is that anywhere else?
No, it's just in the second equation, right?
Yeah, I guess so.
So then we need to get that NaBr from that second equation. But look, this is 2 NaBrs and we only need 1. So what do we need to do?
Do we need to divide that one in half too?
Yeah, that's right. We do. And we're not exactly sure how we're going to use it. We haven't really thought it all out yet, but we know we're going to need that half of NaBr somewhere. I'm not seeing NaBr anywhere else. Do you?
No.
All right, so I'm going to write down here 1/2 of water plus 1/2 of the CaOCl2 plus 1/2 of the NaBr. No, sorry, not 1/2, right?
Why not?
Well, because it's 2 already, right?
Oh, yeah, okay, so 2 divided by 2 is just 1.
That's right. And then the products here, what are they? Why don't you tell me?
2 NaCl. So just 1 NaCl.
That's right, because we divided it by 2.
Plus 1/2 of the calcium hydroxide.
That's right, 1/2 of the calcium hydroxide.
And then the Br.
Oh, yeah, there's one more there. So 1/2 of the Br. Did I do that right? The bromine gas or bromine liquid there.
Yeah.
So what's the delta H associated with this equation?
Is it it's like negative 30.1, right?
That's right, just divided by 2, so negative 30.1. And notice I didn't change the signs there, right? Because you only change the signs if you're reversing the reaction. Okay, so what do we do with that third equation?
Why do we need that third equation?
Well, do we not? If we just add these two together, is it going to give us our final equation there?
It's going to give us 1/2 chlorine gas.
What about this thing over here?
Yeah, it's still going to be there, huh? So that's why we need the third equation, I guess.
That's right.
And it looks like we need, what do we need?
Well, we want to get rid of this, right? Because when I add all this together on this side, right? If I could think of this as being all on the left side and all of this on the right side, we do see that these are going to cancel out. Can you see that?
Oh, because it's on the reactants and the product side?
Yeah. Okay. And but that's all. I'm going to be left with the water. I'm going to be left with the calcium oxide. But I don't want those two, right? I want the sodium bromide, right? Because that's what it says here. And I want the chlorine gas, so those are good. But these ones I need to get rid of. This one I already am getting rid of there.
But that's good because the third reaction has the calcium oxide and the water.
That's right. Has the calcium oxide in the water. But it looks like, again, we have to divide it by 2, right?
Yeah, because you only have 1/2 of calcium oxide on the left there.
Very good. So I'm going to write that equation down divided by 2. So 1/2 calcium hydroxide yielding 1/2 calcium oxide and 1/2 H2O. All right. And what's the delta H for this?
Half of 65.1, right?
That's right. So 65.1 divided by 2, 32.6. Okay. So now if I add these three reactions together as I have them written, we saw already that this cancels out, right? And now we're seeing that we have something to cross out the calcium oxide. And anything else that can be canceled out?
Well, everything is going to be canceled out except for the chlorine and the sodium bromide.
That's right. So the water also here, right?
Yeah.
So the water's canceling out there. And then I'm left with the calcium and, well, I have calcium hydroxide here.
Oh, where is it? Oh, yeah, that's on the second one. You can cancel that with the second one.
Very good. So am I left with what I want in the equation?
Yeah, I think so.
Yeah, so 1/2 chlorine gas plus a sodium bromide yields, on this side, a sodium chloride.
Yeah, we want that.
And then the bromine gas. Do we have that?
Yeah, it's right there.
Okay, those are the only two things that are left that are not half a bromine gas. Is that the way it is in the reaction?
Yeah.
Okay. Sorry, not a bromine gas, it's bromine liquid.
Oh, right, yeah.
Okay, so then, and this is the answer to the question, what is the delta H for that reaction?
Well, you just add those numbers, right?
That's right. I got the 55.45, 30.1, and the 32.6. I have to be sure I add them in the right sign. So this value plus a negative 30.1 plus the 32.6, right? So negative 52.95. Okay, did you follow that?
Yeah, I think I got it.
Okay, good job. Okay, so we get a very similar thing here in 7.74. We're going to combine these together in such a way that I can identify the delta H for this reaction. I'm only given two reactions here, and I need to combine them in a way that gives me the delta H for this reaction.
Well, if you add the delta H if you add those two reactions together and add their delta H's, then the product is the new delta H, right?
Yeah. Can I just do that? Can I just add these two together to get this done?
Let me look. You get the 4 NH3s if you add the first one on there, and you get no, this gives you too much oxygen there. And there's no oxygen on the right to get rid of some of that oxygen in the other equation. So, oh wait, the second equation has some NH3, some ammonia in it.
All right, so it looks like we're going to have to add these two together, and the sum of this and this is going to give this, right?
Okay.
Now, how are we going to get 3 oxygens if we have 7 oxygens there?
Oh, well, there's no other oxygen anywhere else, is there?
There isn't. So we have to figure out how to take 7 divided by some value and get 3. So we can do that, a little side algebra, right? 7 divided by x equals 3, right? So we're trying to figure out what number we need to divide it by. So this means 7 equals 3x. X equals 7 divided by 3. So let's throw that number in there. 7 divided by 3, 2.33. Now, how did I know to do that?
Well, the oxygens, that's the only place you're going to get them, right? You're only going to get them from that reaction, the top one.
That's right. I'm only going to get them from here. And so if I need to make this 7 a 3, it looks like I need to divide by 2.33. So let's divide all this up here by 2.33.
What's 4 divided by 2.33?
Well, that's what a calculator is for. It's 1.71. Let's take a look at this a little bit. If I calculate delta for the reaction, yeah. So what am I going to need to do with this second one here? Let's try to get some clues for what we need to do with the second one.
It's the same thing. You got 7 on the top, 7 nitrogens, and you need to get that to 2 nitrogens.
So 7 nitrogens here to get to 2. We could do the same little math over here. 7 divided by some number, x, equals 2.
Yeah, so that's what?
Well, x equals 7 divided by 2. That's 3.5. So if I divided 6 by 3.5.
Maybe if you just keep those numbers so that we can see them.
That's a good idea. That's a good idea. So let's make this first equation 4 divided by 2.33. Let's just keep it like that. That many ammonias. And then 7 divided by 2.33 oxygen gases, because that's 7 divided by 2.33. That's actually 3, right?
Yeah, we did that math over there, right?
Yeah. Okay. So what's next? 4 divided by 2.33 NO2s, and 6 divided by 2.33 waters. Okay? And then from this one here, I mean, I don't know how this is going to work out, right? But it seems that this one we have to divide by, what did we say 7 divided by 2 was?
3.5.
So we need to divide this by 3.5 to make it 2. So let's try to do that. Let's see what happens here, okay? So 6 divided by 3.5, I need to divide the whole thing, right? NO2s. 8 divided by 3.5 ammonias. 7 divided by 3.5 nitrogen gases. 12 divided by 3.5 waters. Okay, so let's see. Is this going to give me anything that works? Anything get to cross out?
Let's see. 4 divided by 2.33 and 6 divided by 3.5 NO2s. Is that the same?
It better be. If it's not, there's no way we can solve this problem, and there's a mistake in the book, right?
Oh, really?
Well, I mean, there's no other equations provided, so how are we going to get rid of some stuff?
Okay, well, let's find out.
So 4 divided by 2.33 is 1.7167. We already did that, right? And 6 divided by 3.5. Lucky, huh?
No, not lucky. They knew.
Yeah, they knew. So our NO2s cancel out there because those are the same values. 4 divided by 2.33 and 6 divided by 3.5, that's the same thing. All right, so anything else that gets to cancel out?
Well, you don't want anything else to cancel out on the left.
Right, so I'm here with this and that and my O2. So I'm going to have NH3. How much of it? We'll figure out in a second. And I'm going to have 7 divided by 2.33 O2s. And we decided that that was 3, right? That's why we did that.
Yeah.
So we have 3 O2s. I have to still put the number in here. Don't let me forget. I'll figure that out in a second. Let's just see how we're doing here. And then on the right, we have water and N2. And 7 divided by 3.55, we said 7 divided by 3.5. Is that 2?
Yeah.
Oh, yeah, that's right. That's why we did it, right? 2 N2s. And this other thing here is 6 times 12 divided by 3.5 divided by 2.33. Do you think that's 6?
Maybe.
All right, let's try it. So let's do this one over here first while we're here. So we need to figure out how many waters there are. I'm going to scoot this over a little bit so we get a little bit of light. We still want to be able to see it. Okay, so 6 times 12. That's on top. That's 72. I'll just write this down right over here in this little space. Divided by, what are the values?
2.33 and 3.5.
2.33 times 3.5. So that's 8.155. So 72 divided by 8.155 is 8.8. Is that close?
No.
8.8 waters. And the NH3 here, let's see if that makes any sense. 4 times, am I missing something here? 4 times 8, that's 32, divided by the 2.333 times the 3.5. So that's 3.91. That's kind of close. But this one over here, did I do that one wrong? Let's try to double check that one. 6 times 12 divided by 2.33 times 3.5. 8.8, yeah. Well, I would say that this was a poorly formed question, that there must be some other reaction that we need to get to finish this up. This one is close to 4 here, but that seems sloppy to be at 3.92. And this water here is not close to 6. It's close to 8. So let's double check and see what they say for this one in terms of the answer. I see what I did wrong. I did my math wrong, right? Because this isn't 6 times 12 divided by 2.33 divided by 3.5. This is 6 over 2.33 plus. You don't multiply these together, right?
Oh, yeah.
Okay, so let's try that again. Let's try that again. 6 divided by 2.33. That's 2.575. 12 divided by 3.5. That's those 3.428. And I take this value and add it to this value here. And that is my 6. All right. So that does equal 6 there. Okay. And then same thing over here. I don't multiply 4 and 6 and then divide by those two, right? Because why?
Because you're adding those fractions, not multiplying.
That's right. So let's get 4 divided by 2.33. 1.71. Let's get 6 divided by 3.5. And so this plus this, now that better equal 4, but it doesn't. Let me try that again. 4 divided by 2.33. And then 6 divided by 3.5. 3.428. And it's supposed to be 4. Oh, no. Oh, no. Sorry, this is the 8 divided by 3.5, not that. This is the NO2. Try that again. 8 divided by 3.5. That's 2.2. So I take this one. This is a 6. No. Where's it at? This one, which same value, well, almost the same value. So that value added to this value here. There we go. That's our 4. Okay, very good. Now we're not done yet, right?
Why not?
Well, we haven't found the delta H's yet. What's the delta H for this first reaction?
Oh, it's 1132, negative 1132 divided by 2.33?
That's right. So negative 1132, that's from the reaction by itself, but I divided everything by 2.33. So I'm finding the delta H for this reaction divided by 2.33, right?
Yeah, because that's what you did.
Right. So the answer is negative 485.2. And for this one down here?
Negative 2740 divided by 3.5?
That's right. Negative 2740 divided by 3.5. So that's a delta H for this reaction equals negative 782.9. So I'm combining these two together to get the new delta H. So I'm going to get this one plus this one. And the answer is a negative 1268. Negative 1268. Okay, very good. So, next one. All right, so 776. Which of the following thermochemical equations can have a delta HF? What does that little f mean?
What do you mean?
See the delta HF here in the equation, the question.
Oh, that F? I don't know.
Remember, that's delta H of formation. Delta H of formation. A formation reaction. Do you remember what that means?
Oh, when you make the chemical from its elements.
That's right. It's a chemical reaction where we're taking elements and we're creating a chemical. So for the delta H formation reaction, the formation reaction of water, right? If I'm forming water, for example, from its elements, which would be what?
Hydrogen and oxygen, I guess.
That's right. And so we choose those elements how they occur naturally, which is hydrogen gas and oxygen gas, right? Now we have to make sure the equation is balanced, all right? And so if I was going to balance this equation typically, I'm going to rewrite it over here to show you what I would do typically. O2, H2O, I would go something like this. I would see, oh, I need 2 oxygens on the right, put a 2 here, and then that makes a need of 2 more hydrogens. So I put a 2 there. And so then I see that I have a balanced equation. That's how I would do a typical balancing equation. However, and that's fine. However, to be a delta HF formation reaction, you only produce 1 mole of the material that you're making. All right? So in this reaction, how many moles of material do you produce?
1 mole.
No, see, there's a 2 there.
Oh, 2 moles of water.
Yeah, so this is not a delta HF formation reaction because it's not a formation reaction. I always call it delta H of formation. The delta H of formation is the delta H associated with the formation reaction. This is not a formation reaction because the definition that we've set up for ourselves is just to make 1 mole of the material. So to balance it where I just make 1 mole of the material, I don't put a coefficient here. I just put coefficients or even fractional coefficients here to make it produce 1 mole. So in this case, I have 2 hydrogens on both sides and I have 2 oxygens on the left, and I can reduce that number of oxygens by putting a 1/2 there. Okay, so now this is an equation that's balanced, but you'd only use fractional things under certain circumstances, and a formation reaction is one of those scenarios. Okay, so whatever the delta H is associated of this reaction makes it the delta H of formation, because this is a formation reaction. So we're going to look at these and try to identify which one of these is a formation reaction. Is A a formation reaction?
Now tell me what again a formation reaction is?
It's a reaction where elements are combined to form a mole of a material. And you can only form one product, right? Because formation reactions are tabulated in a table, and people go and find in the table how much energy it takes to make a mole of that material. Okay? So, what do you think?
Well, A is not from elements. It's from some compound to a different one.
That's right. In fact, it's just taking this aqueous to solid. So this is not a formation reaction because it's not from its elements.
B is from its elements.
Yeah, good. You see B there is from its elements. But there's a problem here with N, 2N, and 4H. What's wrong with it?
I don't know.
Well, that's not how you find nitrogen naturally. How do you find nitrogen?
Oh, you mean it's diatomic?
That's right. It should be N2, like this, right? So for this one, to make it a formation reaction, you would need oxygen gas, because that's how you find oxygen gas, nitrogen gas, and hydrogen gas. And then you're producing one of these, NH2, 2. So then you balance it, right? 4 hydrogens, 2 nitrogens, so just a 1 there, 1 oxygen, so you only need you want a half there, 1 carbon. So that would be a formation reaction. And the delta H for this reaction, we could call the delta H of formation. Okay, so B is not a formation reaction. How about C?
It's from elements, and they're nitrogen gas, oxygen gas, hydrogen gas. Ooh, that looks pretty good.
Yeah, it does. Yeah, I think that is a formation reaction. I think you're right. Okay, what about D? Is that a formation reaction?
It's from elements as well. So yeah, it looks good. It's forming this. Isn't it the same as that first reaction, C?
What's the difference between C and D? Are they both formation reactions?
I guess D just has no fractional coefficients.
That's right, or it has a 2 here. But the problem with D is this number.
Why? Why is that a problem?
Because remember, a formation reaction is from its elements, but it's only forming...
Oh, yeah. It's only forming 1 mole of the stuff.
That's right, and we got 2 moles formed here. So only C is going to be a good example of formation reaction. And the delta H for that would be the delta H of formation. You'd have delta H's for these other reactions, but they wouldn't be considered delta H of formations because those are not formation reactions. Okay, good. All right, so here's another problem where we get to practice our understanding of formation reactions and what delta H of formation means. And if you don't understand what delta H of formation means, then go back to 7.76, and we have a good discussion about what formation reactions mean there. So we want to create formation reactions for all of these different compounds. All right. Now, this isn't very difficult because what is a formation reaction again?
You're combining just elements, the elements as they would be naturally, right?
Naturally, or another way of saying that is as their standard state, how they would occur at standard temperature, room temperature, and standard pressures. All right. So for this first one here, the product is going to be that compound, right? Acetic acid, HC2H3O2, right, as a liquid. And one more thing, we always want to make how much of the product?
Oh, just 1 mole. Just 1 mole.
That's right. So HC2H3O2. Very good. So what are the elements that I need here?
Well, you need hydrogen, you need oxygen, you need carbon.
Very good. So I can go carbon, hydrogen, and oxygen. Like that?
Don't you need a 2 there?
Where?
On the oxygen.
You mean down here?
Yeah.
Why would I need a 2 there?
Well, didn't you just say...
Yeah, I know. I'm just kidding. You need it there. Why do you need that?
Because that's the way oxygen is found in nature. That's its standard state.
That's right. Very good. Now, do I need to put some more hydrogen on here because I get hydrogen in 2 places?
I don't know.
Now, you don't need to do that, right? You can take the hydrogen from here as well. But we do need to balance this now. And I want to make sure that when I'm balancing, I don't put any numbers in here because the definition of a formation reaction, again, is that I'm only making 1 mole of this material. So what do I need to balance it?
Well, you need 2 carbons, 4 hydrogens.
Okay, 4 here.
No, just 2.
And then anything else?
No, that should be it.
All right, good. Now, what is the delta H for this reaction, which it's a formation reaction, so I can call it delta H of formation?
I don't know. How do we know?
Well, it says table 7.2. Table 7.2 is going to show us what this reaction is. So let's bring in table 7.2 and see how we use it. So here's that table 7.2, and what it's titled is Standard Enthalpies of Formation for these typical substances. All right, so this isn't an inclusive of every substance in the world in our book, but it's true that there are tables out there for lots and lots of materials because people have figured this out, learned this from various chemical reactions. You don't actually have to perform these chemical reactions, you know, because like we saw before, if you can find the delta H's for a handful of different reactions and then add them or subtract them or manipulate them in any way you can to find out what the formation reaction is, then you can learn that information. All right. But after you learn it once, tabulate it, put it in a table somewhere, and then everybody can look at it and know it. So we're looking on this table for acetic acid, HC2H3O2. Do you see it on there?
No, I think I saw it. It was down below there, right?
Let's see.
Is it over there?
Yeah, right here, right there. HC2H3O2, liquid, negative 487. And so what does that negative 487 mean?
This process releases 487 kilojoules.
That's right, 487. And then it says up here the units, right? What are those units?
Oh, kilojoules per mole.
That's right, kilojoules per mole, which can also be written as the way they're writing it there, right? Kilojoules moles to the negative 1, right? That's just in the same way as writing that. We've discussed that before, but just in case that's something you didn't catch before. All right. And it's always per mole because delta H of formation reactions only produce 1 mole of material. All right, let's put that off to the side for a second. And, oh, whoops, we're on the wrong one there. There it is right there. Ethyl alcohol. Let's do the same thing now, but make it for the delta H reaction for ethyl alcohol.
Oh, so we got carbon, hydrogen, and oxygen again.
Very good. So it's like this same thing here, right? I'm going to write it again because I guess we don't know if it's the same number of materials, right? C2H5OH. So this time we have only 1 oxygen. So we need to put a 1/2 there. We have 4 hydrogens still, and we have 2 carbons. All right. And then the delta H for this reaction, it's a formation reaction, so I can put an F on there. Even if I don't put an F on there, the delta H for this reaction is going to be the same value. We call it delta H formation, but there's also delta H of combustion, delta H of decomposition, just whatever the kind of the reaction is, the delta H for it, you can give it a special little nickname, right? A little extra name. All right, let's see if we can find ethanol here.
There it is.
Right here?
Yeah. Negative 238.6.
Very good. Oop. Negative 238.6. Very good. And the next one there.
This one we need calcium, sulfur, oxygen, Do we do the H2O too?
Yeah, we do. Also, the H2O also.
Oh, yeah, sorry, not H2O2. That's hydrogen peroxide, right?
That's right. H2O2 is hydrogen peroxide. H2O also means water as well.
That's not a very funny joke.
I know. Okay. All right. So, what are the elements that we need here?
Calcium, sulfur, hydrogen, and oxygen.
Very good. Hydrogen gas, oxygen gas, sulfur, calcium. All right. There's different ways that you can get chemicals. So sometimes sulfur is in the form of S8, but we'll just leave it as S. That's fine. All right. So how many hydrogens?
You need 2 of those, it looks like.
2 of these hydrogen gases. That's right. How about how many oxygens?
It looks like you need 6 altogether, right?
Yeah, 4 over here and 2 over there. So 6. So I'm going to put a 3 in front of that.
1 calcium, 1 sulfur.
Very good. So CaSO4 dihydrate, calcium sulfate dihydrate. Double checking, just looking back and forth. Looks good. 4, 5, 6. 6. All right, so let's bring in our table here.
It's right there, right?
Yep.
Negative 2021.1.
Very good. Negative 2021.1. Right down here. Okay. Negative 2021.1, is that what we said?
Yeah.
Okay. All right, last one.
Oh, you need sodium, you need sulfur, and you need oxygen gas.
Very good. Combining together, what are our products?
It's just one of those things, right?
Yep, that's right. And then,
2 sodiums,
okay,
2 oxygen gases, and that's it.
very good. Bring back our table here. Find it?
Should be, let's see, Na. Oh, yeah, Na, sorry. There it is, 1384.5.
Good. Negative 1384.5. Okay. All right. Excellent. Next question. All right. So now we're going to use these delta H formation information in table 7.2 to identify the delta H's for some chemical reactions that are not delta H formation reactions.
I thought that the delta H formations were only producing 1 mole on that table.
That's right. But the way that we use them, here, let me bring up our table of delta H formation reactions. So here, okay, 7.2. This gives us information about how much energy is associated with making 1 mole of hydrogen peroxide. This table gives us information about how much energy is associated with making 1 mole of water. And this table also, well, it doesn't talk about O2. Now, why doesn't it list, well, it might list it up here, but notice that on this table down here, all of the elements like lead, sulfur, right, chlorine gas, iron, all of them are 0, right, because there's no energy associated with the formation of these things, because this is how you find them naturally, right? Energy only releases or is absorbed upon the formation of chemicals, right? And if your elements are forming chemicals, then typically those are going to be only bond-forming reactions, therefore they're always going to release energy.
If they're always going to release energy, why are some of the delta H formations positive?
So like C2H4, for example, 52.284, it's a positive value.
Yeah, why is that?
Well, let's look at the delta H formation for that reaction. C2H4, to form that, what do we need?
Carbon and hydrogen.
Very good, carbon and hydrogen gas, right?
And you need 2 hydrogens.
2 of the hydrogen gases.
And 2 carbons.
Very good. So the delta H formation for this is not a negative value. It requires energy, 52.284. And so the question is, why? What's going on there? Well, the answer is that the energy associated with breaking these two hydrogen bonds, right? Because what this is two of these. The energy associated with breaking that is more than the energy associated with forming these bonds. All right. So the bonds that are formed here are going to be relatively weak bonds. So this process requires energy to form that compound. So sometimes in formation reactions, you do need to break bonds because you're dealing with diatomic compounds. And if the bonds that are being formed are not as strong, then you will actually require energy. But most of these are going to be negative, meaning that the process releases energy, because in general, you're usually from elements forming many more bonds than you're breaking. Okay? So get that out of the way. Now we can answer this question. How much energy is associated with the formation of H2O2? Let's look on here and see if we can find H2O2. I found it.
Where's it at?
Right here.
Oh, yeah, negative 187.6.
Very good. H2O2, negative 187.6. That's how much energy is associated with what?
Making hydrogen peroxide from its elements.
That's right. So if I wanted to make 2 moles of hydrogen peroxide, how much energy would that release?
Would that be just times 2?
That's right. Negative 187.6 times 2. So to make 2 moles of hydrogen peroxide, it releases 375.2 moles of, kilojoules of energy to make 2 moles of hydrogen, to make 2 moles of hydrogen peroxide. To decompose 2 moles of hydrogen peroxide, it's just the opposite of that number. It's just the opposite of this number, right? So it's not negative 375.2, it's positive 375.2. That is how much energy it takes to take these 2 moles of hydrogen peroxide and break them down into their elements. All right? So that's how this will be useful. What I do is I take the delta HF formations for my elements. So here's my hydrogen peroxide. It's negative 187.6. I have to multiply that by 2, though, because I have 2 moles of it. All right? This is reacting, decomposing, really, because there's no other chemicals it's reacting with. It's just breaking down into water and oxygen gas. 2 waters and oxygen gas. Well, I could look at how much energy is associated with the formation here of water, and that's down here at the bottom. Okay, so what's the delta H of formation?
Is negative 241.8.
Look closer there.
What, 241.8?
Yeah, but see how this is water with an L, and there's 2 waters down here.
Oh yeah, gas and liquid. So it's negative 285.9.
Yeah, so there is a difference there. It does depend on the state, because if you are forming something in the gas, then that means some of the energy had to go into evaporating that water from liquid to gas. And that's why the amount of energy that you get out of the process is less, because some went into the evaporation. All right, and for oxygen gas, it's 0, right? Because that's its element. It already has its elements, so I'm going to put 0 there. Now, what you do to identify the delta H for this reaction is you find out how much energy was associated with the making materials, products, and you subtract the energy associated with decomposing this material. So putting that negative sign in there, or essentially it's products minus reactants. And with that minus sign in there, you're changing the sign on everything that's in the product side. So it's like identifying how much energy was associated with breaking down those materials into their elements. So products, that's the 2 times the 285.9. Negative 571.8. And that's all because I don't have to do anything with the oxygen there. And then products minus now the 2 times the negative 187.6. Okay, so Let me scoot this table out of the way for a second. 2 times negative 187.6. I'm going to change that sign there. So negative 571.8 minus that value there. That's going to give me a negative 196.6. All right, so that's the energy, the delta H, for that chemical reaction. Again, I used my table, looked at the energy associated with the formation of all of these compounds, and then I took products, put in the negative sign there to change these to positive, because now that's the energy associated with decomposing all those bonds, right? All right, and then the result is the delta H for that reaction. Okay, let's do that second one there.
Can I see the table?
Yes, we need the table, don't we?
Okay, so where's NaCl? NaCl, there it is. Negative 411.0.
That's right. So is it okay if I write the chemical reaction down?
Okay, if you want to.
Where's my mouse? Move this out of the way. I'll write down the chemical reaction here. We got, let me get a new fresh piece of paper. We got HCl plus NaOH, NaCl, and water. And we just found NaCl was negative 4. Did I do that right? Oh, no, NaCl is over here. Negative 411.0. Only one of them.
Yeah, and then water, what was that? Was negative 285.9. It says down there, as I can see it.
Yeah. Negative 285.9.
So those are our products.
Right. And we do products minus reactants.
Reactants, HCl. I don't see HCl on there.
Let's see if it's on here somewhere. Do you see it yet?
Yeah, oh, there it is, 92.3.
Very good. Negative 92.3. And sodium hydroxide.
Is it down below a little bit? There it is, negative 426.8.
Very good. Negative 426.8. I don't need that negative sign in there. Oh, that was from, I made a mistake there. Okay, so now products, products, negative 411.0 plus negative 285.9 minus negative 92.3 plus negative 426.8. All right, just using some math, right?
Yeah, I guess so.
Okay, so we're always using math in chemistry because chemistry is applied math. Okay, let's get this up here so we can see the calculator a little bit better. Still can't see it very well, huh? There we go. Okay, so I'm going to do products. Negative 411 plus negative 285.9. All right. And then I'm going to do the reactants. Negative 92.3 plus negative 426.8. Okay. Was water 426.8? I'm looking at that. That doesn't seem like I copied down the right number. Where did I get that number? Oh, no. This is products. This is reactants. That's right. Okay, so now all I have to do is I have to finish up this here where I take products, 696.9, minus reactants, 590.1. So a negative 177.8 for this chemical reaction up here. H equals negative 177.8 kilojoules. Okay, very good. All right, 782 here. The value for the standard heat of combustion, right? So that's just again, the delta H for some combustion reaction. Do you remember what combustion means?
Oh yeah, it was a long time ago, but it's like organic compounds reacting with oxygen or something?
Yeah, it's just burning, right? So let's get a little piece of scratch paper here and remind ourselves of what a combustion reaction looks like. It's going to look something like this: CXHY, maybe O, maybe N, maybe not Z, combining with oxygen gas. And what are the products of combustion?
Carbon dioxide and water.
Very good. Carbon dioxide and water. All right. So that's a combustion reaction. So any delta H associated with that will be the delta H of combustion. All right. And now when you talk about the delta H of formation, again, it's 1 mole that you're forming. If you're talking about a delta H of combustion, then you're going to be combusting 1 mole of the material. All right. So the value for the standard heat of combustion, and if you forget that, you can always just look at what it says here. It says this is the value, kilojoules per mole, right? So it's per mole of material, it says right there. So we write the thermochemical equation for the combustion of 1 mole of sucrose and calculate the value of delta H of formation for this compound. The sole product for combustion is, again, like you said. So sucrose, chemical formula, C12H22O11. All right, C12H22O11. Sucrose combusting. So what do I combine it with?
Oxygen gas.
That's right, oxygen gas. And then what are our products?
Carbon dioxide and water.
Very good. Carbon dioxide and water. All right. And now we're going to use table 7.2 to tell us what the heat of reaction, how much heat is released or required in this reaction. I think we know it's going to be released because we eat sugar and that's where we get our energy. So we must be getting that heat from the combustion. Now, we don't talk about combusting sugar in our bodies, right? Have you ever taken any biology classes?
Yeah, I took some stuff. Let's see, like respiration?
That's right, respiration. When we eat food and breathe air, that process is the consuming, harnessing the energy, the heat energy from the sucrose that we eat. Specifically, usually we talk about glucose because sucrose is broken down into glucose and fructose. Sucrose is a molecule that contains 1 unit of glucose and 1 unit of fructose. Anyway, let's balance this.
Oh, okay. 12 carbon dioxide on the right.
All right, let's start with that. 12 carbon dioxide, that gives us 12 carbons.
11 waters for the 22 hydrogens.
11 here, or?
Oh, no, not 11.
That would be 11 times 2. That's right, isn't it?
Oh, yeah, okay, that's right.
So 11 waters. Now I have 22 hydrogens. How many oxygens do I have altogether here?
Let's see, 24 on the left.
24 over here.
And 11 on the right. So 34, 35 altogether. But then on the left, you have 35 minus 11, right? Because you have 11 over there.
That's right. And so we're trying to find out what coefficient goes there, right?
Yeah, so 35 minus 11.
So 35 minus 11 is 24.
So 12?
That's right. 12 can go in there. Let's see. Did that work out? Let's do our little accounting thing to make sure we're seeing the right amount of material. How much carbon on the left?
12.
On the right?
12.
How much hydrogen on the left?
22.
And how much on the right?
22.
How much oxygen on the left?
24, 34, 35.
Okay, very good. And on the right?
24 plus 11, yeah, 35.
Okay, very good. So we got to balance the equation. All right. Now to use the table to find out what the there it is, good. What the delta H of this reaction is, right? We need to find.
Oh, I see glucose.
You see glucose?
I thought I did. Well, no, I guess I don't.
So we need to find sucrose in here, right? C12H22O11. Let's see, anywhere?
I'm not seeing it in there.
Let's see, what can we do here? Write the sole product, calculate the delta H of formation for this compound.
Oh, the delta H of formation.
Oh, sorry. The delta H of formation. Well, what we're going to do then to calculate the delta H of formation for this compound is use the delta H for this reaction. They gave us the delta H for this reaction.
Oh yeah, negative 5.6 stuff.
That's right. Negative 5.65 times 10 to the third, or in other words, 5650 kilojoules of energy. So this reaction has that. And now the delta H of formation for carbon dioxide is on their table here.
Yeah, it's right there, negative 393.5.
Very good. Negative 393.5. So negative 393.5, but there's 12, right? Water.
Is that liquid water?
Yes, liquid water right there.
Okay, so it's negative 285.9.
Negative 285.9. So this is 11. These are the products. 11 of negative 285.9s. Very good.
And then we don't know the reactants.
That's right. We don't know the reactants here. But we do know the products. I've written the products. I should have written the products on the left because it's supposed to be products minus reactants equals, and in this case we know what it equals. It equals the negative 5650. So I'm going to write here as the X, which is my reactants, which is just this. Now oxygen doesn't matter, right? Because why?
That's how it is elementally.
That's right. That's how it is in its standard state. So there's no energy associated with that. Okay, so negative 5,650 here. We're going to put those two in our calculator there. 12 times negative 395, negative 393.5, sorry, times 12. There's a value. Negative 285.9 times 11. All right, so those are our products. So I'm going to take those values there and add them together, and that's my total for my products. Negative 7,867 minus reactants equals negative 5650. So I'm going to add this to both sides. So I have negative 5650, but I'm going to add 7867 to both sides here. And that's going to equal 2,217, but that's the negative x. So x is going to equal negative 2,217. So, whoops, lost us down there at the bottom. So this is the delta H of formation. It must be because the delta H of formation for the reactants would go in here. So that's how we get that. Good job, Fred.
I think I'm going to have to watch that one again to understand it.
That's right. Go back and watch yourself. You're the movie star.
All right, yeah, thank you.
Have a good day.
Bye-bye.